There's a monster hiding in the darkness of space. It's been there for billions of years, growing silently, a galaxy that would make ours look like a tiny speck of dust floating in an ocean. They told us there were limits to how large things in the universe could grow. They were so wrong. If you love learning about the incredible mysteries of our universe, please subscribe to the channel. You'll join a community of curious minds exploring the cosmos together. Now let's get started. Imagine standing at one end of the Milky Way. If you could somehow travel at the speed of light, it would take you 100,000 years to reach the other side. That's traveling at almost 300,000 kilometers per second, and it would still take you 100 millennia to cross our home galaxy. The sheer size of that journey is almost impossible to comprehend. You'd pass billions upon billions of stars. You'd witness nebulae where new stars are being born, black holes tearing matter apart, and planetary systems we can only dream of exploring. But here's where things get truly wild. Alcyoneus is so large that if you started that same journey across its length at light speed, you wouldn't arrive at the other end for over 16 million years. Let me say that again, 16 million years. That's not the age of the galaxy. That's not how long it's been around. That's simply how long it would take light itself to travel from one end to the other. To put this in perspective, 16 million years ago on Earth, our ancestors weren't even human yet. They were early apes just beginning to walk upright. The entire story of human civilization, from the first cities to the moon landing to you watching this video right now, all of that history is just a tiny blip compared to the time it would take to cross this galaxy. And here's the thing that keeps me awake at night. We almost missed it entirely. In February of 2022, a team of astronomers led by Martijn Oe, a PhD student at Leiden University in the Netherlands, was analyzing data from the low-frequency array telescope, called LOFAR for short. They weren't specifically looking for giant galaxies. They were just mapping the radio sky, collecting signals from distant cosmic objects. LOFAR is special because it detects radio waves, not visible light, and it sits in a carefully protected nature reserve in the Netherlands, where radio interference from cell phones and other technology is deliberately blocked. The researchers were looking through thousands of radio images when something caught their eye. Two enormous plumes of plasma, stretching out into space like the arms of an inconceivably vast cosmic giant. At first, they thought it might be an error, a glitch in the data, because structures this large simply weren't supposed to exist. But it wasn't an error. It was real. They named it Alcyoneus, after a giant from Greek mythology. The name is fitting. In the ancient stories, Alcyoneus was one of the Gigantes, the giant offspring of Gaia, who fought against the Olympian gods. The mythological Alcyoneus was considered the greatest of all giants, king of the Gigantes. Now, that name belongs to the greatest giant in our cosmic neighborhood, a structure so vast it redefines what we thought was possible. Now you might be wondering, what exactly are we looking at when we see Alcyoneus? Is it just a really big blob of stars? Not quite. Let me paint you a picture of what's actually happening out there, 3 billion light years away from Earth. At the heart of Alcyoneus sits a galaxy that, on its own, wouldn't seem particularly special. It's an elliptical galaxy, which means it's shaped more like a football than a flat spiral like our Milky Way. Inside that galaxy, at its very center, lurks something terrifying and magnificent, a supermassive black hole. Now, black holes are often misunderstood. People think they're like cosmic vacuum cleaners, sucking up everything around them. But that's not quite right. Black holes are extremely powerful, yes, but they're also surprisingly organized. And when you're talking about a supermassive black hole, one that weighs millions or even billions of times more than our sun, You're talking about an object that doesn't just affect its immediate surroundings, it shapes the entire galaxy. Here's what happens. As matter falls toward the black hole, it doesn't just disappear quietly into the darkness. It spirals inward, forming what we call an accretion disk. The friction and compression in this disk heat the material to millions of degrees. It glows brilliantly in multiple wavelengths of light. But not all of that matter makes it into the black hole. Some of it gets caught up in the black hole's intense magnetic fields, twisted and accelerated until it's moving at a significant fraction of the speed of light. And then, like water from a fire hose, that material gets blasted out into space in two narrow jets, streaming away from the black hole's poles in opposite directions. These jets are extraordinary. They're made of plasma, which is matter so hot that electrons have been ripped away from their atoms. This plasma races outward, carrying enormous amounts of energy. As it travels, it crashes into the thin gas that exists between galaxies, the intergalactic medium. The collision creates shockwaves, heats up the surrounding space, and generates powerful radio emissions. That's what LOFAR detected. Those radio waves have been traveling through space for 3 billion years, and when they finally reached Earth, they told us the stories of something incredible. The two jets from Alcyoneus extend outward for at least 8.1 million light-years in each direction. When you add them together, you get a minimum total length of 16.2 million light-years. And that's a conservative estimate, a lower bound based on what we can actually see. Think about that for a moment. Our Milky Way is 100,000 light-years across. You could line up 162 Milky Ways end-to-end, and they still wouldn't span the length of Alcyoneus. If you wanted to build a model where the Milky Way was the size of a penny, Alcyoneus would stretch longer than 4 meters. But here's where the story gets even more fascinating, and this is the part that has astronomers scratching their heads. Alcyoneus isn't what we expected. For decades, scientists have had theories about what makes giant radio galaxies grow so large. They call these galaxies GRGs, short for giant radio galaxies, and before Alcyoneus, we'd found hundreds of them scattered across the universe. These are galaxies with radio jets extending for millions of light-years. But Alcyoneus is the champion, the largest we've ever found. And speaking of scales that are hard to wrap your mind around, the challenge of traveling across such enormous cosmic distances is exactly why I made a video explaining the real reason generation ships will never work. If you've ever wondered whether humanity could actually travel to distant star systems in massive spacecraft, I break down the physics, the engineering problems, and the biological challenges that make it far more complicated than science fiction suggests. The link in the description. So, back to our cosmic giant. Scientists used to think that for a galaxy to grow jets this large, it needed certain special conditions. Maybe the central black hole had to be exceptionally massive. Maybe the galaxy needed to be in a sparse region of space where there wasn't much gas to slow down the jets. Maybe the galaxy itself had to be particularly big and bright. But when the team studied Alcyoneus closely, they found something surprising. The host galaxy is relatively normal. It's not exceptionally massive. The black hole at its center, while certainly supermassive, isn't unusually large compared to other galaxies with similar jets. And Alcyoneus isn't sitting in an empty void. It's in a fairly typical cosmic environment, surrounded by other galaxies in what astronomers call a filament, one of the thread-like structures that make up the cosmic web. So why is it so big? That's the mystery. That's what makes Alcyoneus so important to science. You see, when you find something that breaks your expectations, that's when you learn the most. If Alcyoneus followed all the rules we thought we understood, It would just be another data point confirming what we already knew. But it doesn't. It tells us that our models are incomplete. There's something we're missing about how these cosmic giants grow. One possibility is time. Maybe Alcyoneus has simply been active longer than most other radio galaxies. Black holes don't fire their jets continuously forever. They turn on and off based on how much matter is falling into them. If there's plenty of gas and dust swirling around the black hole, the jets are powerful. But if the black hole runs out of fuel, the jets can shut off, sometimes for millions of years. Alcyoneus might have had an unusually long and stable period of activity, allowing its jets to plow through space for tens or even hundreds of millions of years without interruption. During that time, the jets just kept pushing outward, creating the enormous structure we see today. Another possibility is the environment. Even though Alcyoneus isn't in a completely empty region of space, maybe the intergalactic medium around it is just slightly less dense than average. That would mean less resistance for the jets, allowing them to travel farther before their energy dissipates. Or maybe there's something else entirely, something we haven't thought of yet. Maybe the magnetic fields in the area are oriented in just the right way. Maybe there was a past collision with another galaxy that triggered an extra powerful burst of jet activity. Maybe the black hole's spin is perfectly aligned to maximize the jet's power. The truth is, we don't know yet. And that's what makes this so exciting. Science isn't about having all the answers. It's about asking better questions. Every time we discover something like Alcyoneus, we're reminded that the universe is far stranger and more complex than we imagined. We're reminded that our little corner of space, our little galaxy, our little planet, is just one piece of an incomprehensibly vast cosmic puzzle. Now, let's zoom out for a moment and talk about what these giant radio galaxies actually tell us about the universe as a whole. You see, galaxies aren't isolated islands floating randomly through space. They're connected. They influence each other. They shape the cosmic web, that magnificent large-scale structure that organizes matter across billions of light years. And supermassive black holes, despite being relatively tiny compared to their host galaxies, play an absolutely crucial role in this cosmic dance. When a supermassive black hole fires its jets into intergalactic space, it's not just creating a pretty radio image for astronomers to study, it's fundamentally changing the environment around it. Those jets carry enormous amounts of energy. When they slam into the intergalactic medium, they heat up the gas to millions of degrees. That hot gas becomes much harder to compress, which means it becomes much harder for it to collapse and form new stars. In other words, supermassive black holes act like cosmic thermostats. They regulate star formation not just in their own galaxy, but potentially in neighboring galaxies millions of light years away. This is called feedback, and it's one of the most important processes in modern astrophysics. Without feedback from black holes, galaxies would convert all their gas into stars far too quickly. The universe would look completely different. There might not be enough gas left over to form planets. There might not be enough time for life to evolve before all the stars burned out. So in a very real sense, the fact that you're here watching this video, breathing oxygen on a planet orbiting a medium-sized star, is partly thanks to supermassive black holes regulating the cosmic environment billions of years ago. Alcyoneus takes this idea to an extreme. Its jets extend so far that they're affecting space on truly cosmic scales. The energy pumped into the intergalactic medium by these jets is staggering. We're talking about something like 10 to the power of 45 joules of energy. To put that in perspective, that's about as much energy as our sun will emit over its entire 10 billion year lifetime, all concentrated into those two narrow jets. And that energy doesn't just disappear. It ripples outward through space, creating bubbles and cavities in the intergalactic medium. It influences how gas flows through cosmic filaments. It might even affect the formation of other galaxies millions of light years away. When you start to think about it this way, you realize that nothing in the universe exists in isolation. Every black hole, every galaxy, every star is part of an interconnected web of cause and effect stretching across billions of light years and billions of years of time. We are not separate from this process. We are part of it. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was forged inside stars that lived and died billions of years ago. Those stars formed from gas clouds that were shaped by galactic winds and black hole jets. The very atoms that make up your body were once part of the cosmic web, drifting through the same intergalactic medium that Alcyoneus is now heating with its jets. You are made of stardust. You are a way for the universe to know itself. And when you look at an image of Alcyoneus, you're not just looking at something distant and disconnected from your life. You're looking at part of the same grand cosmic story that created you. Now, let's talk about how we actually discovered this thing, because the technical achievement here is just as impressive as the galaxy itself. LOFAR, the low-frequency array, is not your typical telescope. When most people think of telescopes, they picture a giant dish or a tube with lenses pointed at the sky. LOFAR is different. It's what we call a radio interferometer, which means it's actually made up of thousands of smaller antennas spread across Europe. The main core of the telescope is in the Netherlands, but there are LOFAR stations in Germany, France, the United Kingdom, Sweden, Poland, and several other countries. These stations work together, combining their signals to create a virtual telescope much larger than any single antenna could be. The farther apart the antennas, the sharper the image they can create. This technique, called interferometry, is incredibly powerful. It's like having a telescope the size of an entire continent, and it allows astronomers to see details in radio sources that would be impossible to detect otherwise. But there's a catch. The data processing required to combine signals from thousands of antennas spread across thousands of kilometers is absolutely massive. We're talking about petabytes of data, millions of megabytes that need to be carefully synchronized and analyzed. The computers have to account for the exact position of each antenna, the rotation of the Earth, the interference from satellites and human technology, and countless other variables. It's a monumental task, and it's only possible because of advances in computing power and sophisticated algorithms developed over decades of work. When Martin Oe and his team processed the LUFA data, they were using a sky survey called LUTI-SS, the LUFA 2-meter sky survey. This survey aims to map the entire northern sky at radio wavelengths, creating a detailed census of radio sources across the cosmos. It's painstaking work. Each tiny section of sky has to be observed for hours, the data has to be processed, artifacts have to be removed, and the final images have to be carefully analyzed. In the particular dataset where Alcyoneus was found, the team was looking at a region of sky that contained thousands of galaxies. Most of them showed up as tiny points or small smudges of radio emission. But when they looked more closely at one particular spot, they saw those two enormous lobes extending outward like cosmic wings. At first, they had to verify that what they were seeing was real. Could it be two separate galaxies that just happened to line up? Could it be an artifact of the telescope's processing? They checked and double-checked. They looked at the spectrum of the radio emission to confirm it was consistent with a single source. They measured the alignment of the two lobes to make sure they were perfectly opposite each other. which is what you'd expect from jets coming from a single black hole. Everything checked out. This was real. This was one structure, and then they had to measure it. That's harder than it sounds, because radiolobes don't have sharp edges. They fade gradually into the background, so astronomers have to decide on a threshold, a minimum brightness level below which they won't count the emission as part of the galaxy. Different thresholds give you different sizes. The team used standard techniques to estimate the size, and they arrived at a minimum projected length of about 5 megaparsecs. Now, a megaparsec is a unit astronomers use for truly vast distances. 1 megaparsec equals roughly 3.26 million light-years, so 5 megaparsecs is about 16.3 million light-years. But here's something important to understand. That's the projected length, meaning that's how long it appears from our viewpoint here on Earth. Remember, we're looking at this galaxy from a single angle. We can't circle around it to see it from different perspectives. So if the galaxy is tilted relative to our line of sight, the actual length could be even greater. Imagine looking at a pencil lying on a table from directly above. It might look 4 inches long, but if you tilt the pencil so it's pointing slightly away from you, it might only look 3 inches long from your viewpoint, even though the pencil itself hasn't changed size. The same principle applies to Alcyoneus. The 16 million light-year measurement is what we can confirm for certain, but the true length could be significantly larger. Think about that. The largest structure we've ever seen created by a single galaxy might be even larger than we think. Now, you might be wondering, are there other galaxies out there even bigger than Alcyoneus that we just haven't found yet? The answer is probably yes. You see, finding giant radio galaxies is incredibly difficult. First, you need a sensitive radio telescope that can detect faint emissions across a wide area of sky. Second, you need the patience to observe large portions of the sky for long periods. Third, you need the computing power to process all that data. And fourth, you need a bit of luck. Radio galaxies are relatively rare to begin with. Most galaxies don't have powerful jets, and among those that do, most have jets that extend for only hundreds of thousands or a few million light-years. To find something like Alcyoneus, you need all the right conditions. The galaxy has to be oriented so we can see both lobes. It has to be bright enough for our telescopes to detect, and it has to be in a part of the sky we've actually observed. The universe is enormous. Even with our most powerful surveys, we've only observed a tiny fraction of all the galaxies out there. There are probably billions of galaxies in the observable universe, and we've studied in detail maybe a few million of them. That means there's a huge amount of cosmic real estate we simply haven't explored yet. As our telescopes get better and our surveys cover more of the sky, we're almost certain to find even larger structures. There might be a galaxy out there with jets extending for 20 million light-years or 30 million or more. We just haven't found it yet, and that's one of the most thrilling aspects of astronomy. Every time we build a better telescope or develop a new technique, we discover things we never expected. The universe keeps surprising us. Just think about how much our understanding has changed over the past century. In the 1920s, we didn't even know other galaxies existed. Most astronomers thought the Milky Way was the entire universe. Then Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to observe what were then called spiral nebulae. He found certain stars in these nebulae whose brightness varied in a predictable way, and by measuring their periods of variation, he could calculate their distance. The results were shocking. These nebulae weren't clouds of gas within the Milky Way. They were entire galaxies, millions of light-years away. Suddenly, the universe expanded from one galaxy to billions. Then in the 1930s and 40s, astronomers started detecting radio waves from space. They built the first radio telescopes and discovered that the universe was far more active and violent than anyone had imagined. There were objects out there emitting enormous amounts of energy in radio wavelengths, far more than could be explained by stars alone. By the 1960s and 70s, we began to understand that these radio sources were powered by supermassive black holes. We developed the theory of active galactic nuclei, the idea that intensely bright cores of some galaxies were actually accretion disks around black holes millions or billions of times more massive than the Sun. And now, in the 21st century, we're mapping the radio sky in unprecedented detail, finding structures like Alcyoneus that challenge our assumptions about what's possible. Each generation of astronomers thinks they've got the universe figured out, and each generation is humbled by the next discovery. That's the beauty of science. It's not about ego or being right. It's about being less wrong over time. It's about refining our models, asking deeper questions, and remaining open to the possibility that everything we think we know might need to be revised. So when we look at Alcyoneus, we should feel a sense of awe, yes, but also a sense of humility. This galaxy is a reminder that the universe is under no obligation to make sense to us. It operates on scales and timescales that dwarf human experience, and yet, somehow, we tiny beings on a small rocky planet have figured out how to detect and measure something 16 million light-years across, located 3 billion light-years away. That's remarkable. That's worth celebrating. Now, let's dive deeper into the physics of what's actually happening with those jets, because the mechanisms at work here are absolutely fascinating. When material falls toward a supermassive black hole, it doesn't fall straight in, because everything in space has some angular momentum, some sideways motion. The material spirals inward, forming a disk. This is the accretion disk I mentioned earlier, and it's an incredibly complex and violent place. The inner parts of the disk orbit faster than the outer parts, just like planets closer to the Sun orbit faster than planets farther away. This difference in orbital speed creates shear forces, friction between adjacent layers of the disk, and friction generates heat. Enormous amounts of heat. In the innermost regions of the accretion disk, temperatures can reach millions or even billions of degrees. At these temperatures, atoms are completely ionized, ripped apart into a soup of electrons and nuclei. This is plasma, the fourth state of matter, and it behaves very differently from ordinary gases. Plasma is electrically conductive, which means it can carry electric currents and interact strongly with magnetic fields. And around a spinning black hole, magnetic fields can become extraordinarily powerful. Here's where it gets really interesting. As the accretion disk rotates, it drags magnetic field lines around with it, twisting them up like the strands of a rope. These twisted magnetic fields can build up enormous amounts of energy. Eventually, that energy has to go somewhere, and it gets channeled along the rotation axis of the black hole. Perpendicular to the accretion disk, this is where the jets form. Charged particles, electrons and protons, get caught in these magnetic field lines and accelerated to incredible speeds. Some of these particles reach velocities approaching 99% of the speed of light or even higher. When particles move that fast, Einstein's special relativity tells us that strange things start to happen. Time slows down for them, their mass effectively increases, they carry enormous amounts of kinetic energy. These ultra-fast particles blast outward in narrow beams, creating the jets we observe. And because the process is happening at both poles of the black hole simultaneously, you get two jets pointing in opposite directions, exactly what we see with Alcyoneus. Now, as these jets travel outward through space, they don't just fly through a perfect vacuum. Space isn't truly empty. Between galaxies, there's a thin gas called the intergalactic medium, or IgM. It's incredibly tenuous, with densities far lower than the best vacuum we can create in laboratories on Earth. But over distances of millions of light years, even this thin gas becomes significant. When the jet plows into the IgM, it's like a supersonic aircraft creating a shock wave. The jet pushes the gas aside, creating a cavity. The compressed gas at the edge of this cavity glows in radio wavelengths, creating the bright lobes we detect with radio telescopes. But here's something that puzzles scientists. The jets from Alcyoneus have traveled over 8 million light-years in each direction. At close to the speed of light, you might think that journey would take about 8 million years. But there's a complication. The jets aren't continuous streams like water from a hose. They're more like bullets fired from a machine gun. The black hole doesn't maintain a perfectly steady outflow. Instead, it releases blobs of plasma in pulses. Each blob travels outward, slams into the material ahead of it, and creates a shock wave. These shock waves can actually travel faster than the individual particles in the jet, carrying energy outward even more efficiently. This is called a relativistic jet, and the physics involved is mind-bendingly complex. You have to account for special relativity. Because the particles are moving so fast, you have to account for magnetohydrodynamics, the study of how magnetic fields interact with ionized gases. You have to account for particle acceleration, shock physics, radiation processes, and the interaction with the surrounding medium. Scientists use supercomputers to simulate these jets, and even with our most powerful computers, we can only approximate what's happening. The full picture is still beyond our complete understanding. But what we do know is this: the amount of energy required to create and maintain jets like those of Alcyoneus is staggering. We're talking about the conversion of matter into energy through the process of accretion onto a black hole, with an efficiency that can reach 10 to 20%. Let me explain what that means. When you burn gasoline in a car engine, you convert maybe 25 to 30% of the chemical energy into useful work. The rest is lost as heat. When you run a nuclear power plant, you convert less than 1% of the mass of uranium into energy through fission. But when matter falls into a black hole, up to 10 or even 20% of its mass can be converted into energy through the accretion process. That makes black holes the most efficient engines in the universe. Nothing else comes close. To power jets like those of Alcyoneus, the central black hole has to consume matter equivalent to millions or even billions of suns over the course of its active lifetime. That material comes from gas in the surrounding galaxy, from stars that wander too close and get torn apart, from smaller galaxies that merge with the host. Every bit of matter that falls in contributes to the energy budget, and over millions of years, all that accumulated energy gets channeled into those two magnificent jets. Now, here's something that will really make you think. The light we're seeing from Alcyoneus, those radio waves detected by LOFAR, started their journey toward Earth 3 billion years ago. 3 billion years. When that light left Alcyoneus, Earth was a very different place. There were no humans, there were no dinosaurs, there weren't even any animals on land. Life existed only in the oceans, and it consisted mostly of simple single-celled organisms. The most complex life forms were maybe some early multicellular creatures and primitive algae. The radio waves from Alcyoneus have been traveling through space for 3 billion years. During that time, continents drifted across Earth's surface, mountains rose and eroded away. Ice ages came and went. Life evolved from simple cells into an explosion of diversity. Plants colonized the land. Animals followed, forests grew, Species evolved, thrived, and went extinct, and all the while, those radio waves were crossing the vast emptiness of space, carrying information about a galaxy so far away that its light takes 3 billion years to reach us. When those photons finally arrived at Earth and were collected by LOFAR's antennas, they told us their story. They told us about a supermassive black hole, about jets of plasma, about a structure 16 million light-years across. They told us about events that happened when our planet was still in its geological adolescence. This is what I mean when I say astronomy is time travel. Every time we look at a distant object, we're not seeing it as it is now. We're seeing it as it was when the light left. The farther away something is, the further back in time we're looking. Alcyoneus as we observe it today might not even exist anymore. In the 3 billion years since that light started traveling toward us, the jets might have shut off. The galaxy might have merged with another galaxy. The structure might have faded and dispersed into the intergalactic medium. We have no way of knowing what Alcyoneus looks like right now in real time because that information won't reach us for another 3 billion years. By the time it does, humanity might be long gone, or we might have evolved into something unrecognizable, or we might have spread across the stars. The universe operates on timescales that make human lifetimes seem like the blink of an eye. And yet, here we are, able to piece together the story of cosmic giants that existed billions of years ago. We do this through careful observation, rigorous mathematics, and the collaborative effort of thousands of scientists working across generations. This is what science gives us. Not just facts and figures, but perspective, a sense of our place in the grand sweep of cosmic history. You are not just a person living in a particular time and place. You are a pattern of atoms organized in such a way that the universe can contemplate itself. The atoms in your body were forged in stars. The light entering your eyes left distant galaxies billions of years ago. Your thoughts, your consciousness, your sense of wonder at reading about Alcyoneus, all of this is the universe experiencing itself. Carl Sagan said it beautifully, "We are a way for the cosmos to know itself." When you look at an image of Alcyoneus, you're participating in that cosmic self-awareness. You're part of the process by which the universe comes to understand its own nature. Now, let's talk about what finding Alcyoneus means for the future of astronomy and our search for even more extreme cosmic structures. The discovery of Alcyoneus was made possible by LOFAR, but it's just one of many next-generation radio telescopes that are revolutionizing our view of the universe. There's the Meerkat telescope in South Africa, which consists of 64 dish antennas working together. There's the Australian Square Kilometre Array Pathfinder, ASCAP, which is mapping the radio sky in the southern hemisphere. And there's the big one coming, the Square Kilometre Array itself, or SKA. The SKA is a truly international mega project. When completed, it will be the largest and most sensitive radio telescope ever built. It will consist of thousands of antennas spread across Africa and Australia, working together to create a collecting area of 1 square kilometre, hence the name. With the SKA, we'll be able to detect radio sources fainter and farther away than ever before. We'll map the distribution of hydrogen gas throughout the universe, tracing how galaxies formed and evolved over cosmic time. We'll detect gravitational waves from colliding black holes. We'll search for signs of extraterrestrial intelligence in ways that were impossible before. And we'll almost certainly find more giant radio galaxies. Structures even larger than Alcyoneus might be out there, waiting for us to discover them. But radio astronomy is just one piece of the puzzle. We're also entering a golden age of space-based telescopes. The James Webb Space Telescope, launched in December of 2021, is already sending back breathtaking images of the distant universe. Webb can see in infrared wavelengths, which allows it to peer through dust clouds and observe the first galaxies that formed after the Big Bang. The Nancy Grace Roman Space Telescope, scheduled to launch later this decade, will have a field of view 100 times larger than Hubble's, allowing it to survey vast areas of sky and discover countless new galaxies, supernovae, and exoplanets. The European Space Agency's Euclid mission, which launched in 2023, is mapping the geometry of the dark universe, studying how dark matter and dark energy have shaped the cosmic web over billions of years. And there are ground-based telescopes too. The extremely large telescope being built in Chile will have a primary mirror 39 meters across, making it the largest optical telescope ever constructed. With it, we'll be able to directly image exoplanets, study the atmospheres of distant worlds, and observe galaxies at the edge of the observable universe with unprecedented clarity. All of these instruments, working together across different wavelengths of light, are giving us a more complete picture of the cosmos than we've ever had before, and each new discovery raises new questions. Why do some galaxies produce giant radio jets while others don't? What determines how long those jets remain active? How do these jets affect the formation of stars in nearby galaxies? How do supermassive black holes grow to become so massive in the first place? These are the questions keeping astronomers awake at night. And Alcyoneus is providing crucial clues. One of the things that makes Alcyoneus so valuable scientifically is that it challenges our assumptions. Before its discovery, astronomers had certain ideas about what conditions were necessary for giant radio galaxies to form. They thought you needed a particularly massive black hole, or a particularly massive host galaxy, or a particularly empty region of space. But Alcyoneus doesn't fit those criteria. Its host galaxy is fairly ordinary. The black hole, while supermassive, isn't exceptional, and the environment, while not densely packed with other galaxies, isn't unusually sparse either. So what gives? Why did this particular galaxy grow such enormous jets? One hypothesis involves something called the duty cycle of active galactic nuclei. Black holes don't stay active forever. They turn on when there's gas available to fall into them, and they turn off when the fuel runs out. The active phase might last for millions or tens of millions of years, followed by a quiet phase that could last hundreds of millions of years or longer. Most of the giant radio galaxies we've found probably represent multiple episodes of activity. The black hole turns on, produces jets for a while, then shuts off. Later, more gas falls in, perhaps from a merger with another galaxy, and the black hole turns on again. Each episode adds to the total size of the radio lobes. Alcyoneus might have had an unusually stable and prolonged period of activity, or it might have had several episodes perfectly timed to build upon each other. Without more detailed observations, we can't say for certain. Another factor might be the age of the jets. Radio emission fades over time as the high-energy electrons in the plasma lose their energy through radiation. So the outer parts of Alcyoneus's lobes, the parts farthest from the galaxy, are probably much fainter than the regions closer to the core. If the jets had shut off millions of years ago, we might only be able to see a fraction of their total extent. The fact that we can see the lobes all the way to their outer edges suggests that the jets might still be active, or at least were active relatively recently on cosmic timescales. That means we might be catching Alcyoneus at a special moment in its life, while its jets are near their maximum extent. But there's another possibility that's even more intriguing. Maybe Alcyoneus isn't special at all. Maybe there are lots of galaxies with jets this large or larger, and we just haven't found them yet because they're too faint or in regions of sky we haven't surveyed. If that's the case, then Alcyoneus isn't telling us about rare and unusual conditions. It's telling us that our understanding of typical galaxy evolution is incomplete. It's telling us that the influence of supermassive black holes extends much farther than we previously thought, and that has profound implications for cosmology, the study of the universe as a whole. You see, when we try to understand how the universe evolved from the hot, dense state of the Big Bang to the rich tapestry of galaxies and clusters we see today, we rely on computer simulations. We input the laws of physics, the initial conditions from the early universe, and we let the simulation run forward in time to see what happens. These simulations have gotten incredibly sophisticated. They can reproduce many features of the real universe, the cosmic web of filaments and voids, the sizes and shapes of galaxies, the distribution of dark matter, but they're not perfect. There are still discrepancies between what the simulations predict and what we actually observe. One of the biggest challenges is getting the simulations to produce realistic galaxies. If you just let gravity do its thing, galaxies in the simulations end up too massive and too densely packed with stars. They don't match what we see in the real universe. The reason for this mismatch is feedback. The simulations need to include processes that regulate star formation, that prevent all the gas in a galaxy from turning into stars too quickly. And one of the most important feedback mechanisms is energy injection from supermassive black holes. When a black hole fires jets into its surroundings, it heats up the gas, making it harder for that gas to cool down and collapse into stars. This is called AGN feedback, where AGN stands for active galactic nucleus. It's a crucial ingredient in modern cosmological simulation. But here's the thing, most simulations only account for AGN feedback on relatively small scales within the galaxy itself, or perhaps a few 100,000 light-years beyond. They don't typically account for jets extending for millions of light-years, affecting the intergalactic medium on truly cosmic scales. Alcyoneus suggests that we might need to rethink this. If jets can extend for 16 million light-years or more, then AGN feedback might be affecting the universe on much larger scales than we've been modeling. That could change our understanding of how galaxies form, how gas flows through the cosmic web, and how the large-scale structure of the universe evolved over time. This is why a single discovery, one galaxy out of billions, can be so important. It's not just about the object itself, it's about what that object tells us about the underlying physics governing the entire cosmos. And it reminds us, yet again, that we still have so much to learn. Let's take a moment to appreciate the sheer improbability of us being able to study something like Alcyoneus. First, consider the physics. We needed the universe to produce supermassive black holes, which required the formation of the first stars and galaxies. We needed those black holes to grow to millions or billions of solar masses, which required complex processes of gas accretion and galaxy mergers over billions of years. We needed the right conditions for those black holes to fire jets, which required the alignment of magnetic fields, rotation, and fuel supply. Then, consider the observational requirements. We needed the galaxy to be oriented so that we could see both lobes from Earth. If we were looking at it edge-on, along the axis of the jets, we'd only see one lobe or possibly just the core of the galaxy. We needed the jets to be active recently enough that the radio emission hasn't faded completely. We needed the galaxy to be in a part of the sky that our telescopes could observe, and we needed the technological development to detect it. Radio astronomy only began in the 1930s. Interferometry techniques that allow us to combine signals from multiple antennas were developed over decades. The computational power needed to process LOFAR data only became available in recent years. The specific sky survey that found Alcyoneus only started in the 21st century. If we'd been looking 100 years ago, we wouldn't have found Alcyoneus because we didn't have radio telescopes. If we'd been looking 50 years ago, we wouldn't have found it because our instruments weren't sensitive enough. If we'd been looking 20 years ago, we wouldn't have found it because the computational techniques to process the data didn't exist yet. Everything had to align perfectly. The universe had to create this structure. We had to develop the right technology. We had to look at the right patch of sky at the right time with the right instruments. And somehow, against all odds, we did. That's the miracle of scientific discovery. It requires patience, persistence, creativity, and a bit of luck. But when it happens, when we uncover something new about the universe, it's one of the most exhilarating experiences humanity can have. Now, I want to talk about something that doesn't get discussed enough: the human side of astronomical discovery. When you read about Alcyoneus in the news or in scientific papers, it's easy to think of it as an abstract finding, just data and numbers. But behind every discovery are real people with real stories. Martin Oey, the lead researcher, was a PhD student when he found Alcyoneus. Think about that. He wasn't a senior professor with decades of experience. He was a young scientist, probably in his 20s, working on his doctoral thesis. He was spending long hours analyzing data, writing code, running simulations, trying to make sense of radio images that often look like fuzzy blobs of noise. Finding Alcyoneus wasn't just intellectually exciting for him, it was potentially career-defining. Major discoveries like this can establish a young scientist's reputation, opening doors to future research opportunities, collaborations, and funding, but it also came with pressure. Once you find something extraordinary, you have to verify it. You have to make absolutely sure you haven't made a mistake. Because if you announce a major discovery and it turns out to be wrong, it can damage your credibility. So Oey and his team had to carefully check and double-check their work before going public. They had to measure the size of the lobes multiple times using different methods. They had to rule out the possibility that it was two separate galaxies coincidentally aligned. They had to analyze the spectrum of the radio emission to confirm it matched what you'd expect from jet-powered lobes. They had to calculate the distance to the galaxy using its redshift, the stretching of light wavelengths caused by the expansion of the universe. All of this takes time and meticulous effort. And it's done in collaboration with other scientists, each bringing their own expertise. The paper announcing the discovery of Alcyoneus had 11 co-authors from institutions across Europe. That's how modern astronomy works. It's a team effort, and it's not just the scientists directly involved in the discovery. There are the engineers who designed and built LOFAR. There are the technicians who maintain the antennas and keep them running smoothly. There are the software developers who write the code to process the data. There are the funding agencies and taxpayers who make the research possible. There are the educators who inspired the scientists when they were students. Every discovery is built on the contributions of countless people, many of whom will never receive public recognition. But their work is essential. This is the human side of astronomy. It's not just about abstract cosmic phenomena. It's about curiosity, collaboration, dedication, and the shared human desire to understand our place in the universe. And it's about inspiration. When young people hear about discoveries like Alcyoneus, some of them feel that spark of wonder that leads them to pursue careers in science. Maybe a teenager watching this video right now will become the astronomer who discovers an even larger galaxy in 20 years. Maybe you'll be the one who solves the mystery of why these giants grow so large. Science is a relay race across generations. Each generation hands the baton to the next, building on what came before while asking new questions and developing new tools. So when we celebrate the discovery of Alcyoneus, we're not just celebrating one galaxy or one research team. We're celebrating the entire scientific enterprise, the collective human effort to understand the cosmos. Now, let's think about what else might be out there that we haven't discovered yet. Alcyoneus is the largest galaxy we've found so far, but the universe is full of surprises. There are almost certainly structures out there that are even more extreme, even more mind-bending. Consider quasars. These are the brightest objects in the universe, supermassive black holes actively feeding on enormous amounts of matter. The energy output from a single quasar can outshine an entire galaxy containing hundreds of billions of stars. We've found quasars so distant that their light has been traveling toward us for over 13 billion years, meaning we're seeing them as they were when the universe was less than 1 billion years old. How did black holes grow so massive so quickly after the Big Bang? That's one of the biggest mysteries in astrophysics right now. It challenges our understanding of how structure formation works in the early universe. Then there are fast radio bursts, FRBs. These are mysterious pulses of radio energy that last only milliseconds but release as much energy as the sun emits in several days. We've detected hundreds of them, and we still don't fully understand what causes them. Some might be from magnetars, incredibly dense neutron stars with powerful magnetic fields. Others might be from processes we haven't even thought of yet. There are gamma-ray bursts, the most energetic explosions in the universe besides the Big Bang itself. When a massive star collapses to form a black hole, or when two neutron stars collide, they can produce a jet of gamma rays so intense that if one occurred in our galaxy and happened to be pointed at Earth, it could strip away our ozone layer and cause mass extinctions. Fortunately, these events are rare and usually occur in distant galaxies, but they remind us that the universe is a violent place on cosmic scales. There are rogue black holes wandering through intergalactic space, kicked out of their home galaxies by gravitational interactions during mergers. There are hypervelocity stars traveling so fast they'll eventually escape the Milky Way entirely. There are dark matter halos, invisible structures that outweigh visible galaxies by factors of 10 or more, detectable only through their gravitational effects. And then there's the cosmic web itself, the largest structure in the universe. If you could zoom out and see the entire observable universe at once, you'd see that galaxies aren't randomly distributed. They're organized into filaments and sheets like a three-dimensional spider web stretching across billions of light years. Between these filaments are enormous voids, vast regions of space containing very few galaxies. The cosmic web is shaped by dark matter and dark energy, two mysterious components that make up 95% of the universe. We don't know what dark matter is made of. We don't know what dark energy is at all. We just know they exist because of their gravitational effects. Dark matter holds galaxies and clusters together. Without it, galaxies would fly apart. Dark energy is causing the expansion of the universe to accelerate. Distant galaxies are moving away from us faster and faster, and eventually, billions of years from now, they'll be receding so quickly that their light will never reach us. The universe we can observe is shrinking in a sense. Future civilizations, if they exist, will look out at the night sky and see fewer galaxies than we do. They might not even realize that the universe is expanding because all the evidence will have literally moved beyond their cosmic horizon. This is why astronomy is so urgent. We live in a special time, a window in cosmic history, where we can still observe the afterglow of the Big Bang, still detect distant galaxies, still piece together the story of how the universe evolved. But let's bring it back to Alcyoneus and what it represents. This galaxy is a monument to the power of gravity, magnetism, and nuclear forces operating over cosmic timescales. It's a reminder that the universe builds structures on every scale, from atoms to superclusters, and each scale reveals new physics, new beauty, new mysteries. When you look at an image of Alcyoneus, you're seeing 16 million light-years of space transformed by the energy of a single black hole. You're seeing matter in its most extreme state, accelerated to near-light speed, heated to millions of degrees, organized by magnetic fields into narrow jets that dwarf our entire galaxy. You're seeing the consequences of events that happened 3 billion years ago, when Earth was barely recognizable, when the most complex life was still confined to the oceans, when the continents were arranged in configurations we can barely reconstruct. And you're seeing proof that human beings, despite our tiny size and brief lifespans, can comprehend the universe. We can measure the immeasurable. We can imagine the unimaginable. We can take electromagnetic radiation that's been traveling through space for 3 billion years and use it to reconstruct the history of a galaxy we'll never visit. That's extraordinary. That's worth pausing to appreciate. So often in our daily lives, we get caught up in small concerns. We worry about deadlines, bills, relationships, all the mundane details of existence. And those things are important, of course. They matter to us as individuals. But sometimes it's valuable to zoom out, to remember that we live on a planet orbiting an ordinary star in an ordinary galaxy, in an ordinary part of the universe. To remember that we're made of atoms forged in stellar furnaces, that we're the product of 4 billion years of evolution, that we're part of a cosmic story that began nearly 14 billion years ago and will continue for trillions of years into the future. When you hold that perspective, it can be humbling, but it can also be empowering. It reminds you that you're part of something vast and ancient and magnificent. It reminds you that every breath you take, every thought you think, is a miracle of complexity arising from simple physical laws operating over deep time. You are a way for the universe to know itself. And that's not just a poetic sentiment, it's literally true. The atoms in your brain were once scattered across interstellar space. They came together through gravity, chemistry, and the quirks of planetary formation. They organized themselves through the process of evolution into patterns capable of thought, consciousness, wonder. When you contemplate Alcyoneus, those atoms are arranging themselves into neural firing patterns that represent a galaxy 3 billion light-years away. Information that traveled across a third of the observable universe is now encoded in the structure of your brain. You are, in a very real sense, holding the universe within your mind, and that connection goes both ways. Not only are you made of stardust, but your existence affects the universe, however slightly. Every thought you have, every action you take, sends ripples outward through space and time. The heat from your body radiates as infrared photons that will travel through space forever. The gravitational influence of your mass, infinitesimal as it is, affects the motion of every other object in the universe. You are not separate from the cosmos, you are part of it. And the cosmos is part of you. This is what astronomy teaches us if we're willing to listen. It's not just about galaxies and black holes and radio telescopes. It's about perspective, connection, and our place in the grand scheme of things. Now, let's talk about what the future holds for research on giant radio galaxies like Alcyoneus. The discovery in 2022 was just the beginning. Since then, astronomers have been conducting follow-up observations with multiple telescopes, trying to learn as much as possible about this cosmic giant. They're studying the spectrum of the radio emission in detail, looking for clues about the age of the jets and the composition of the plasma. They're measuring the magnetic field strength in the lobes by analyzing how the radio waves are polarized. They're searching for X-ray emission, which would tell them about the hottest gas in the system. They're looking at optical and infrared images to study the host galaxy itself, measuring its mass, age, and star formation rate. All of this data will help refine our models of how giant radio galaxies work. And the more examples we find, the better we'll understand the full range of possibilities. Already, since the discovery of Alcyoneus, astronomers have found several other extremely large radio galaxies, none quite as large as Alcyoneus, but close. This suggests that there's a population of these cosmic giants out there, and we're only just beginning to catalog them. As new radio surveys come online, particularly with the Square Kilometre Array, we expect to find thousands more giant radio galaxies. We'll be able to study them statistically, looking for patterns and correlations. Do they preferentially form in certain environments? Are they more common at certain epochs in cosmic history? Is there a maximum size that jets can reach, or can they grow arbitrarily large given enough time? These questions will keep astronomers busy for decades to come. And there's a broader context too. Understanding giant radio galaxies helps us understand galaxy evolution in general. Every galaxy with a supermassive black hole at its center is potentially capable of producing jets. The fact that only some do, and only at certain times, tells us something important about the life cycle of galaxies. Most galaxies, including our own Milky Way, are currently quiet. The supermassive black hole at the center of our galaxy, called Sagittarius A star, is relatively dormant right now. It's not producing powerful jets, but it might have in the past, and it might again in the future. In fact, we have evidence that Sagittarius A star was much more active in the past. There are structures called the Fermi bubbles, enormous lobes of high-energy gamma rays extending above and below the plane of our galaxy, stretching for about 25,000 light-years in each direction. These bubbles were likely created by a burst of activity from our galaxy's central black hole a few million years ago. If our own galaxy can produce structures like that, imagine what it might look like if Sagittarius A star became as active as the black hole in Alcyoneus. Our galaxy could develop jets extending for millions of light years. Of course, we'd be inside the galaxy, so we wouldn't see it the same way we see Alcyoneus. But observers in distant galaxies would see the Milky Way transformed into a giant radio galaxy. This raises an interesting point about perspective. We tend to think of galaxies as having fixed properties, as being certain types. We classify them as spirals, ellipticals, irregulars. We call some of them radio galaxies, some quasars, some Seyfert galaxies. But these classifications are really just snapshots of galaxies at particular moments in their lives. A spiral galaxy can become an elliptical through a merger. A quiet galaxy can become an active galaxy when gas falls into its central black hole. And an active galaxy will eventually become quiet again when the fuel runs out. Galaxies are dynamic, evolving systems. They change over time. And the changes can be dramatic. Alcyoneus is currently in an active phase, producing jets that have reached record-breaking sizes. But billions of years from now, those jets will shut off. The radio lobes will fade. The galaxy will become just another elliptical, indistinguishable from billions of others, except perhaps for some faint remnants detectable only by the most sensitive instruments. And then perhaps another burst of activity will occur. Another galaxy will merge with Alcyoneus, bringing fresh gas to feed the black hole. The jets will fire up again. New lobes will form, possibly overlapping with the old ones, creating a complex structure that tells the story of multiple episodes of activity. This is the life cycle of giant radio galaxies. It's a story of birth, growth, dormancy, and rebirth, playing out over billions of years. And it's all driven by one of the most mysterious and fascinating objects in the universe, the supermassive black hole. Let's take a moment to appreciate just how strange black holes really are. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. The boundary of this region is called the event horizon. Once you cross the event horizon, you're doomed to fall toward the center, toward a point of infinite density called the singularity. At least, that's what general relativity tells us. Einstein's equations predict that all the mass of a black hole is compressed into a single point of zero volume and infinite density. But most physicists don't believe this is literally true. They think that when you get down to extremely small scales, close to the singularity, quantum effects become important, and we need a theory of quantum gravity to fully understand what happens. We don't have such a theory yet. It's one of the great unsolved problems in physics. String theory, loop quantum gravity, and other approaches are trying to bridge the gap between general relativity and quantum mechanics, but we're not there yet. So the center of a black hole remains a mystery. We can describe what happens outside the event horizon with great precision, but inside, we simply don't know. What we do know is that black holes are real. We've detected them through their gravitational effects on nearby stars. We've observed the radiation emitted by gas falling into them. We've even captured images of the glowing accretion disks around supermassive black holes using the Event Horizon Telescope. In April of 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's event horizon, or rather, the shadow it casts against the bright background of the accretion disk. The black hole was M87 star, located in the center of the giant elliptical galaxy Messier 87, about 55 million light-years from Earth. That image was revolutionary. It confirmed predictions made by general relativity over a century ago. It showed that event horizons really exist, that black holes are real physical objects, not just mathematical curiosities. And in May of 2022, the Event Horizon Telescope released a second image, this of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. Even though it's much closer than M87 star, only about 26,000 light-years away, it was actually harder to image because it's much smaller and the gas around it moves and changes on timescales of minutes. Both images showed the same thing, a dark central region surrounded by a bright ring of emission. The dark region is the black hole's shadow, about 2.5 times larger than the event horizon itself due to gravitational lensing effects. The bright ring is light from the accretion disk, bent and amplified by the black hole's intense gravity. These images are incredible achievements. They required coordinating radio telescopes around the world, effectively creating an Earth-sized telescope. They required new algorithms to process the data and reconstruct the images. They required years of painstaking work by hundreds of scientists, and they're just the beginning. Future observations with the Event Horizon Telescope will capture videos of the gas swirling around black holes, showing the dynamics in real time. We'll be able to test general relativity in the most extreme environments in the universe. We might even detect signatures of new physics that Einstein's theory doesn't predict. But here's what's really fascinating. Even though black holes are the most extreme objects we know of, they follow the same physical laws as everything else. They're governed by general relativity, thermodynamics, quantum mechanics, The same principles that govern atoms, stars, and galaxies. Black holes have temperature, though it's incredibly low, fractions of a degree above absolute zero for supermassive black holes. They radiate energy through a quantum process called Hawking radiation, predicted by Stephen Hawking in 1974. Over unimaginably long timescales, far longer than the current age of the universe, black holes will actually evaporate, shrinking and eventually disappearing in a final burst of radiation. Black holes have entropy, a measure of disorder and information content. In fact, the entropy of a black hole is proportional to the area of its event horizon, not its volume. This led to a revolution in theoretical physics called the holographic principle, which suggests that all the information in a three-dimensional region of space can be encoded on a two-dimensional surface surrounding that region. This idea has profound implications for our understanding of space, time, and information. It suggests that the universe might be fundamentally different from how it appears. It's led to new ways of thinking about quantum gravity and the nature of reality itself. And it all started from studying black holes, these bizarre objects that form when massive stars collapse or when matter accumulates in the centers of galaxies. The supermassive black hole in Alcyoneus is one of these remarkable objects. It's not the most massive we've found. That record goes to black holes with masses of tens of billions of solar masses found in the centers of the most massive galaxies. But it's nonetheless an object of almost incomprehensible density and power, all that mass equivalent to hundreds of millions of suns, compressed into a region smaller than our solar system. The event horizon of such a black hole would have a diameter of a few billion kilometers, which sounds large until you realize that's still less than the distance from the Sun to Uranus. And from this relatively tiny region, the black hole exerts influence over 16 million light-years of space through its jets. It's like a cosmic needle threading through the fabric of the universe, stitching together the story of structure formation and galaxy evolution. Now, I want to address something that might be on your mind. When we talk about these extreme cosmic phenomena, it's easy to feel disconnected from them. They're so far away, so unimaginably large, so removed from daily human experience. What does Alcyoneus have to do with your life? It's a fair question, and the answer has multiple layers. On a practical level, astronomy and astrophysics drive technological innovation. The techniques developed to build radio telescopes like LOFAR have applications in telecommunications, medical imaging, and data processing. The algorithms used to analyze astronomical data have been adapted for use in artificial intelligence and machine learning. The engineering challenges of space missions have led to advances in materials science, robotics, and computer technology. GPS satellites use corrections from general relativity to maintain their accuracy. Your smartphone's camera uses technology derived from astronomical imaging. The internet itself grew out of infrastructure built for scientific collaboration. So even if you never think about galaxies or black holes, you benefit from the research that studies them. But there's a deeper answer too. Astronomy changes how we see ourselves and our place in the universe. It provides perspective that's hard to get any other way. When you realize that Earth is a small planet orbiting an average star in an ordinary galaxy, one of hundreds of billions of galaxies, it becomes harder to think that the universe was made just for us. It becomes harder to believe that our petty conflicts and divisions are cosmically important. At the same time, when you realize how rare and precious life might be, how the conditions for complexity and consciousness required billions of years of cosmic evolution, it makes our existence feel more valuable, not less. We are the universe becoming aware of itself, We are away for 14 billion years of cosmic history to contemplate its own story. That's not diminishing, that's elevating. And astronomy teaches us humility. It reminds us that we don't have all the answers, that the universe is under no obligation to make sense to us, that there are mysteries we may never solve. That's okay. In fact, that's wonderful. The universe should be mysterious. It should surprise us. It should challenge our assumptions and force us to think in new ways. The discovery of Alcyoneus is a perfect example. We thought we understood giant radio galaxies reasonably well. Then we found one that broke all the records, and it didn't fit our expectations. It was too large, too ordinary in other ways. It forced us to reconsider our models and ask new questions. That's how science progresses, not through steady accumulation of facts, but through surprises that overturn our assumptions and open new avenues of investigation. And anyone can participate in this. You don't have to be a professional astronomer to appreciate the cosmos. You can look up at the night sky and see the same stars that inspired humans for millennia. You can learn about the latest discoveries and feel that sense of wonder. You can ask questions and think critically about the answers. Science isn't just for scientists, it's for everyone. It's humanity's collective effort to understand the world, and you're part of that effort simply by being curious. So when you hear about Alcyoneus, don't think of it as something distant and irrelevant. Think of it as part of your heritage as a human being. Those radio waves traveled 3 billion years to reach Earth, and you get to know about them. You get to understand, at least in broad strokes, what they represent. You get to participate in the grand story of cosmic discovery. That's a privilege, and it's one we should cherish. Now, let's talk about some of the specific science questions that Alcyoneus is helping us address. One of the big mysteries in extragalactic astronomy is the relationship between supermassive black holes and their host galaxies. We've known for decades that there's a tight correlation between the mass of a galaxy's central black hole and properties of the galaxy itself, particularly the mass of its bulge, the central concentration of stars. This correlation is puzzling because the black hole is tiny compared to the galaxy. The black hole's event horizon is measured in billions of kilometers, while the galaxy spans hundreds of thousands of light years. The black hole contains less than 1% of the galaxy's total mass. So why should there be such a tight relationship? The answer seems to be feedback. The black hole and the galaxy grow together, and they regulate each other's growth through feedback mechanisms. When the black hole is active, it produces jets and winds that blow gas out of the galaxy or heat it up, making it harder for new stars to form. This prevents the galaxy from turning all its gas into stars too quickly. At the same time, processes in the galaxy, like mergers with other galaxies or gravitational instabilities that drive gas toward the center, feed the black hole and make it grow. It's a two-way street, a cosmic dance between the black hole and its host galaxy, playing out over billions of years. Alcyoneus is a perfect laboratory for studying this relationship. Its jets are so enormous that they must be affecting the intergalactic medium over vast distances. Gas that might otherwise fall into nearby galaxies is being heated and pushed around by those jets. This could affect star formation in those nearby galaxies, not just in Alcyoneus itself. In other words, Alcyoneus might be exerting influence over an entire cosmic neighborhood, shaping the evolution of multiple galaxies across tens of millions of light years. This is what we call large-scale feedback, and it's a frontier area of research. Most studies of AGN feedback focus on the galaxy itself or its immediate surroundings. But if jets can remain coherent and powerful over distances of millions of light years, then the feedback extends much farther than we typically consider. This could help resolve some discrepancies between cosmological simulations and observations. Simulations have trouble producing realistic galaxy clusters because they tend to overcool. The gas in the simulations cools down and forms too many stars, creating clusters that are more massive and more tightly packed than what we actually observe. One solution is to inject energy from AGN into the cluster gas, heating it up and preventing overcooling. But the simulations have struggled to get the energy injection just right. Too little and you still get overcooling. Too much and you blow all the gas out of the cluster entirely. Alcyoneus and other giant radio galaxies might be part of the answer. They show that AGN can inject energy over enormous volumes of space, affecting gas on scales much larger than individual galaxies. If we include this large-scale feedback in our simulations, we might get more realistic results. This is still an active area of research, and there's a lot we don't understand. But Alcyoneus is providing crucial observational constraints that will help theorists refine their models. Another question Alcyoneus helps address is the origin and evolution of cosmic magnetic fields. We know that magnetic fields exist throughout the universe, in stars, planets, galaxies, and even in the intergalactic medium. But where did these magnetic fields come from? How did they get there? In the early universe, shortly after the Big Bang, there were probably no large-scale magnetic fields. The universe was too hot and too uniform. But as structure began to form, as gas collapsed to form stars and galaxies, magnetic fields were generated and amplified. One process that generates magnetic fields is called the dynamo effect. When electrically conductive plasma moves in complex, turbulent ways, it can generate and amplify magnetic fields. This is how Earth's magnetic field is maintained, through motions in our planet's liquid outer core. And it's how galaxies generate their large-scale magnetic fields, through turbulent motions in the gas disk. But how do magnetic fields get into the intergalactic medium, the vast spaces between galaxies? One way is through the jets from active galactic nuclei. When jets plow through intergalactic space, they carry magnetic fields with them. The jets themselves are threaded with magnetic field lines, and as they expand and spread, they deposit those fields into the surrounding medium. Over billions of years, as countless galaxies go through active phases, they collectively magnetize the intergalactic medium. The magnetic fields get stirred and mixed by galaxy motions, mergers, and the large-scale flows of gas through the cosmic web. Alcyoneus, with its enormous jets, is contributing to this process on an extraordinary scale. Its jets are seeding 16 million light-years of space with magnetic fields. Future galaxies that form in this region will inherit those fields, incorporating them into their own magnetic field structures. It's a form of cosmic inheritance, where the actions of one generation of galaxies affect the next. By studying the magnetic fields in Alcyoneus's lobes, astronomers can measure the strength and structure of these fields. This tells us about the efficiency of magnetic field transport and helps us understand how the intergalactic medium became magnetized. It's another piece of the puzzle, another clue to how the universe evolved from a smooth, featureless state after the Big Bang to the rich, structured cosmos we see today. Now, let's think about what Alcyoneus tells us about the large-scale structure of the universe. The universe isn't uniform. If you look at the distribution of galaxies on the largest scales, you see a pattern called the cosmic web. Galaxies are concentrated along filaments, thread-like structures that stretch across hundreds of millions of light-years. Where filaments intersect, you get clusters, dense concentrations of thousands of galaxies. Between the filaments are voids, enormous regions of space that contain very few galaxies. These voids can be hundreds of millions of light-years across, Vast empty bubbles in the cosmic foam, this structure formed through the action of gravity on the tiny density fluctuations left over from the Big Bang. Regions that were slightly denser than average attracted more matter through gravity, becoming denser still. Regions that were slightly less dense lost matter to their denser neighbors, becoming emptier. Over billions of years, this process amplified the initial tiny fluctuations into the dramatic structure we see today. Alcyoneus exists within this cosmic web, and its jets are interacting with it. The jets are extending along filaments, following the paths of least resistance through the large-scale structure. Where they encounter denser regions, they slow down and create bright spots in the radio emission. Where they pass through voids, they can travel farther with less resistance. By studying how the jets interact with the cosmic web, we can learn about the distribution of matter in the universe, including dark matter, which we can't see directly, but which dominates the gravitational landscape. This is challenging work because the intergalactic medium is incredibly diffuse and hard to observe. But radio observations of giant galaxies like Alcyoneus provide one of the few ways to study it in detail. There are also broader philosophical implications to discoveries like Alcyoneus. They remind us of the power of scale in the universe. Human beings evolved to understand the world at human scales. We're good at dealing with objects we can see and touch, distances we can walk, timescales we can experience directly. Our intuitions are calibrated for everyday life, but the universe operates on scales that are wildly different from human experience. At the quantum level, particles behave in ways that seem bizarre and counterintuitive. At the cosmic level, space and time bend, galaxies collide, jets extend for millions of light years. Our everyday intuitions fail us at these extremes. You can't rely on common sense to understand quantum mechanics or general relativity. You have to use mathematics, careful observation, and logical reasoning. This is one of the great achievements of science. We've developed methods that allow us to understand realms of nature that are completely foreign to direct human experience. We can comprehend things that are too small to see, too far away to visit, too fast or too slow to perceive directly. Alcyoneus is a perfect example. This galaxy is 3 billion light-years away. Its jets are 16 million light-years long. The black hole at its center has a mass of hundreds of millions of suns compressed into a region smaller than our solar system. None of these numbers are relatable to human experience. You can't visualize them in any meaningful sense. Your brain didn't evolve to handle such scales, but through mathematics and physics, we can understand them. We can write equations that describe how the jets form, how they propagate, how they emit radiation. We can build models that match the observations. We can make predictions that can be tested with future observations. This is the power of the scientific method. It extends our minds beyond the limits of our senses and our intuitions. It allows us to grasp the universe in all its vastness and complexity, and it's deeply humbling. When you realize how much we've learned, and simultaneously how much we still don't know, it instills a sense of both pride and modesty, pride in what humanity has accomplished. We went from looking at points of light in the night sky to understanding that there are other suns, other galaxies, structures billions of light years away. We've mapped the cosmic web. We've detected gravitational waves from colliding black holes. We've imaged the event horizons of black holes. We've found thousands of planets around other stars, all of this in just a few centuries of modern science. It's astonishing. But at the same time, we remain profoundly ignorant about fundamental aspects of reality. We don't know what dark matter is. We don't know what dark energy is. We don't have a theory of quantum gravity. We don't know if we're alone in the universe. We don't know what happened before the Big Bang, or if that question even makes sense. There's so much we don't know. And that's exciting. It means there's still so much to discover. Future generations will look back at our current understanding the same way we look back at medieval cosmology, as a stepping stone on the path to deeper knowledge. Alcyoneus is part of that journey. It's a signpost pointing toward questions we haven't fully answered yet. Why do some galaxies produce such enormous jets? What determines the maximum size a jet can reach? How do these structures affect the evolution of the cosmic web? We have partial answers, hypotheses, models, but we don't have the complete picture yet, and that's okay. That's how science works. You chip away at the unknown, piece by piece, discovery by discovery, building a more accurate and complete understanding over time. Now, if Alcyoneus' scale blew your mind, you need to see the video on the screen. With all those billions of stars packed into galaxies, why is space inside them still so incredibly empty? It sounds like a paradox, but the answer reveals something profound about the nature of the universe itself.